process of cellular respiration under an anaerobic environment, where we're going through a process to oxidize organic molecules and finally produce, ideally, carbon dioxide and metabolic water. That comes a little bit later, that second part, the carbon dioxide and water, particularly in the utilization of the molecular water through the electron transport chain. As we'll come to talk about this oxidative phosphorylation system inside the mitochondria very shortly. But today we're going to be focusing on this guy here, the issue of the citric acid cycle, which is inside the mitochondria. Therefore, we need transporters to bring in fatty acids, to bring in glucose, and bring in amino acids. We'll talk about amino acids, I think, this week in regards to looking at degradation to feed the TCA cycle. The other thing is we produce carbon dioxide in this particular cycle, as well as 1 GTP, which is equivalent to an ATP if we use the ping pong enzyme system. But it is these 8 electrons from every turn of the TCA cycle which basically provides us the electron transport chain to produce this proton gradient. And it is this proton gradient, as we'll see a little later on, which is going to utilize ADP to make ATP, or vice versa, depending on that proton concentration. But we'll talk more about that in coming weeks. So I want to focus on the citric acid cycle today. So it's the fate of the pyruvate that's coming from glycolysis, that 3-carbon constituent. And we're going to see also this fate be substituted by other organic molecules to form acetyl-CoA, but also form intermediates of the TCA cycle, which will directly feed into that cycle. So again, we have a number of positions which we can substitute other molecules, not acetyl-CoA in, but other molecules in regards to fueling this particular cycle. We are mostly going to be focused, as we're going to be looking at glucose today, but later on we're going to be looking at fatty acids and amino acids in regards to how we actually produce acetyl-CoA and how we actually feed them into the TCA cycle. Now, the acetyl-CoA is enzymatically oxidized to carbon dioxide, so this is where we're getting a lot of our carbon dioxide from in the citric acid cycle. And it's these 8 electrons which basically are released as electron carriers in the form of NADH and FADH2. So go back to your lectures. We've already talked about these electron carriers and how they carry those electrons by moving the double bonds on the pi electrons in a number of aromatics. And it's these guys, the NAD and the FADH2, which are then oxidized to basically interact with this system, the oxidative phosphorylation system, to give us this final production of ATP. And this is where we will get most of our ATP from within our cellular system. But we're going to have to contend with this guy first off before we start understanding this one. And again, this is all occurring and happening inside the mitochondria. So the citric acid cycle, Acker-Krebs cycle, or tricarboxylic acid cycle, is basically allowing a entry of a 2-carbon constituent in the form of acetyl-CoA, and it's going to convert that to carbon dioxide. So if you have 2 carbon acetyl-CoA converted to 2 moles of carbon dioxide, so it's a 2-to-2 ratio, okay, or 1-to-1 ratio. The energy release by this oxidation of the acetyl-CoA is in the form of NADH and FADH2, and these are conserved by a reduction reaction. And it's these guys that are now going to be the real important constituents in regards to moving these and using these electron carriers to feed a particular system called the oxidative phosphorylation system. We also generate 1 molecule of ATP in the form of GTP per turn, and this particular pathway is commonly called the hub of metabolism because it's a cyclic pathway, and there's various entry points where other molecules can come in. But as you can see, if we have an entry point here, we may not get the carbon dioxide, or we may get not the carbon dioxide into here because we've gone through the decarboxylational stages on this side, and there's no decarboxylational stages on this side. There's electron movement throughout the pathway, but again, if we skip one of the particular mechanisms and feed it from this way, we may not get the full advantage of the pathway in this region. And it'll become more evident when we start looking at the pathway itself to what I'm actually saying, that by integrating particular metabolism components, we might skip some of the benefits of this particular pathway in a full, complete cycle. And I'll be talking this cycle about being like a watch face. So here's the 12 o'clock position, here's the 3 o'clock position, the 6 o'clock position, and the 9 o'clock position. And we'll be talking about this watch face in regards to the cyclic pathway. The main thing for this particular pathway is this large electron flow to allow us to have that NADH and FADH2 to then freely move to the oxidative phosphorylation system. But also this pathway in a happy cell, when we're going from catabolic to anabolic metabolism and we have enough energy, we're meeting all our demands, we can start using this particular system also to produce precursors for many other biosynthetic pathways. And we can substitute the concentration of these. So let's say when we remove citrate, which is in this number, maybe the 1 o'clock position, we can basically bring this all through, consume acetyl-CoA, bring our friend oxaloacetate here to make citrate, and then move citrate to become then a precursor for a metabolic pathway, not going through the normal face clock interaction. So again, depending on the happiness of the cell and the energy requirements of the cell, or the metabolic requirements of the cell in regards to precursors, we're going to see basically the utilization of this pathway in both manners in regards to catabolism and anabolism. So we're going to see ultimately in the situation where this cellular system is going to be degrading carbon constituents through glycolysis and any other forms to produce large numbers of ATP, and that is where this becomes the hub of life in regards to this metabolic pathway. So let's have a little bit of a think of an overview what I'm talking about. Here we haven't studied amino acids or fatty acids coming into the pathways yet, but these will come into the main system of acetyl-CoA. Here is our pyruvate that we very well know and have studied from glycolysis coming through glucose, and the chain of electrons that are still sinking those NADHs, particularly in this case, and then getting NADH and FADH2 in particular in the citric acid cycle to feed this very large pool of NADH, FADH2, which will then go into the respiratory chain to then produce a lot of ATP at the utilization of consumption of oxygen and producing metabolic water. This system will give us the removal of carbon dioxide in the citric acid cycle. But prior to that, one carbon dioxide moiety is also removed from the pyruvate dehydrogenase complex. So when we're transitioning through the essential pathway, the interlinkage between the pyruvate from glycolysis to acetyl-CoA, we're going to see a removal of a carbon dioxide moiety to give us a 2-carbon constituent. So remember, these are 3 carbon constituents through the pyruvate dehydrogenase complex, which is going to give us an electron carrier because we're going to have to sink that electron somewhere. And then we're going to release one of the carbons in the form of carbon dioxide by this priming step before we produce our 2-carbon constituent of acetyl-CoA, which is then going to feed into the citric acid cycle. So again, this is a clear indication of the complexity and the movement of these electrons, which becomes the main focus of this whole course. So let's have a look in regards to what we're going to see with this pyruvate dehydrogenase complex consuming pyruvate in a commitment stage to form acetyl-CoA, which will then allow us to basically feed the TCA cycle. So let's have a look. We have an additional constituent here. The acetyl-CoA comes into the TCA cycle, but it also has to bind with something and form a new molecule. And it forms a molecule called citrate, but it utilizes our old friend oxaloacetate to do this. So oxaloacetate becomes a very interesting molecule and a focal point in regards to our TCA cycle. We've already been introduced to this particular guy in regards to our producing phosphoenol pyruvate when we're wanting to go through a substrate to allow us to move NADH into the cytosol from the mitochondria, but also giving us this phosphatidyl pyruvate to then move through to produce glucose through gluconeogenesis. But it goes through the form of oxaloacetate, which is being utilized by these various enzymes, consuming carbon dioxide, in this case, if we're going this particular route through the malate shuttle, or if we're using the phosphatidyl pyruvate shuttle, basically consuming CO2, then rearranging and releasing CO2 from the oxaloacetate to give us phosphatidyl pyruvate, which will then substitute the pool within the cytosol from the mitochondria. But again, we're going to get to this situation where we'll see all these particular electron transporters giving this enormous amount of NADH and FADH2 in their reduced carriers and gives the capacity to make ATP. But again, so oxaloacetate becomes an important part in the condensation reaction with oxaloacetate and acetyl-CoA to produce citrate, as we'll see. But as you can also see, there's two moieties of carbon dioxide that come off in the hydrogenase reactions, which we'll have a look at in regards to removing that carbon dioxide and therefore completing the degradation of the acetyl-CoA. But it's going to take several cycles, interestingly, and we'll see this by radiolabel isotope labeling. It'll take several cycles to actually destroy the new moiety of acetyl-CoA coming into the cycle. So we'll have a look at that and follow that by radioisotope labeling, which sometimes actually comes up on the compulsory question in exam number 3 in regards to looking at what happens to a radiolabeled constituent within the TCA cycle and whether it comes off as carbon dioxide as a form of radiolabeled carbon dioxide. And then finally, we're going to be looking at this guy, which is the oxidative phosphorylation. I want you to keep this in mind there where we know where we're going with our FADH2 and NADH carriers. We're actually going to be going to make ATP at the expense of reactive oxygen and making metabolic water. So keep this in mind. FADH2 and NADH is going to be going somewhere, in this case, specifically to make ATP within the mitochondria. So let's go through the first step of the production of acetyl-CoA in regards to the pyruvate dehydrogenase complex. So when you see these dehydrogenase complexes, they're always going to be producing carbon dioxide. And in this case, there's 1, 2, 3 enzymes that are a part of this whole complex in regards to having this capacity to take pyruvate and basically decarboxylate it. And utilizing the thiol ester in the coenzyme A to make acetyl-CoA. So again, we've added that acetyl group to the coenzyme component and look at the energy surplus. We get minus 33.4 kilojoules per mole. So very, very handy reaction. But again, needs to be highly regulated and controlled because this is the gatekeeper from glycolysis into the TCA cycle. So with this particular 3 enzyme complex, we have lipoate, thymine pyrophosphate, FAD, NADH, and CoAsh enzyme, all being cofactors in regards to undertaking this oxidative decarboxylation, because we're going to be removing the carboxyl group and the first carbon of our pyruvate molecule. So remember, this is originally coming from glucose, and we're going to be removing that first carbon constituent and releasing then carbon dioxide. So this is the first issue of releasing carbon dioxide. So the FAD is an electron acceptor. It's going to be reduced to produce FADH2 as an ultimate component, and then NAD plus reduced to NADH, which reoxidizes FADH2. So basically, we've got a little bit of a cycle going on here, but ultimately, we're going to be producing NADH as the primary lever and cyclizing this FADH2 within the enzyme system. So again, that plays a dual role. It's not being released as a product, but it's going to be going through oxidation reduction to work with the NAD plus to do its particular job. The NADH is the one that is the product. So let's have a look. We actually know a little bit about this enzyme through cryo-EM, which is poor man's X-ray crystallography, where basically we see a 3-dimensional structural shape of a protein cluster with E1, E2, and E3. So E1 is the pyruvate dehydrogenase complex. E2 is a dihydrolipotransferacyl transferase and dihydrolipodihydrolase enzyme in this complex. And they're closely coordinated together to ensure that the substrate is moving smoothly between these three complexes. It is no good for the substrate having to actually wander through and go through diffusion in regards to finding its next particular port of call in sense of an enzyme. So by having these closely coordinated and even covalently interfaced with each other, as we see with E1 and E2, it gives us the capacity to have a process of substrate channeling to allow us to move the substrate very closely and very quickly within the system to give us the final product, in this case, acetyl-CoA. Now, the pyruvate dehydrogenase complex has these 5 coenzyme components: niacin, NAD+, the riboflavin, the NAD+, and the PPT, the thymine pyrophosphate. So again, we see some of these particular constituents in our frosted Wheaties in regards to being fortified in our foods to ensure that the key enzyme for interlinkage between glycolysis and the TCA cycle is met with the appropriate requirements to allow us to actually have a functional enzyme. So the pyruvate dehydrogenase complex, this is 3 complex enzymes. So the first enzyme converts the pyruvate to carbon dioxide, and it uses a hydroxyl ethyl derivative of the thymine pyrophosphate to do this. And basically what we see here is basically a oxidation of a hydroxyl ethyl group to form an acetyl group. Now that acetyl group is then handed to the other enzyme using a bound arm, a lipoweight arm that then transfers the chemical functionality of the acetyl group to the next enzyme. With that particular transfer, we see the acetyl-CoA going and consuming coenzyme A to form acetyl-CoA. But the issue is this is not released yet. It's released later when the third enzyme oxidizes this hydrolipate arm, and the sulfide bond is formed and then allows you to pass those electrons through the NAD to the NADH to bring basically the product of NADH, and then causing the release of the acetyl-CoA, which is then the substrate to then feed into the TCA cycle. So with those 3 enzymes, there's a non-reversible approach, and this is why that pyruvate dehydrogenase complex is the gatekeeper between glycolysis and the TCA cycle, because once it's made any of these commitments, there's no way it's going back to produce pyruvate. So here we have our structures, and again, we've come across this before. Here's our coenzyme. We have adenine, a sugar, phosphoanhydride bond, a pantothenic acid, a carbon-based acid, looks a little bit like a peptide bond there. But it's this guy here, the thioreactive group in the mercaptoethylamine, which basically is going to be the constituent where we're going to see that acetyl group coming in and actually binding covalent to this particular group. And again, this is a high energy group, and we get a lot of good energy from this guy. So here we abbreviate this as acetyl-CoA. So here's the CoA component, and we're going to then put the acetyl group in here. So the first reaction is the pyruvate oxidation to acetyl-CoA and carbon dioxide. We cause that release of the carbon dioxide, produce the acetyl-CoA through the pyruvate dehydrogenase complex 1, 2, and 3. Let's have a little closer look at what's going on with that particular complex. So we have the first part of the enzyme head in regards to the first reaction, which is going to take the PPT, or the thymine pyrophosphate, and attach a part of the pyruvate molecule to that particular carrier. In that particular step, this is the rate limiting step. It's highly specific, and what we're going to see is the reduction and removal of this carbon dioxide on binding of that particular ethyl group in regards to the hydroxyl ethyl group being attached to the TPP. With that, we get carbon dioxide release, and the TPP is primed to then move it to this acyl lipolysine moiety. So this normally has a disulfide bond here. So here we have the oxidized disulfide bond on this lipolysine. And when we're going to have this presented, it's going to actually cause the reduction and the sinking of electrons into breaking this disulfide bond and protonating one of the thiols to produce, from a thiolate to produce the thiol. The other component is going to hold on to the CH3O CO in regards to the acetyl group that has come originally from the pyruvate in the form of a thiol ester bond. But we can now replace this thiol ester bond utilizing coenzyme A and allowing us to displace this particular thiol ester bond and swapping it over. In that particular case, the acetyl-CoA then is attached to the coenzyme and then becomes acetyl-coenzyme A. So this guy here, and this is what we want. But in the same process, we have to reprime the enzyme through the acyl lysine in regards to going through and reducing this particular, having this reduced bond to become oxidized, to therefore we can then take on more of the hydroxyethyl TPP constituent that's coming from the pyruvate. In this case, what we do with that darn thiols, we form a disulfide bond by cycling the electrons that are needed to break off that particular proton and those electrons to give us that disulfide bond, that covalent bond between the two thiols. And we do that importantly by cyclizing NAFADH. And they will be sinking both two of the electrons and two of the protons into this particular system, allowing us then to form the oxidized lipoenzyme that we're needed for the pyruvate dehydrogenase complex number 1, E1. So again, we have these three parts of the enzyme: the transport system in regards to attaching it to the thiol ester, the generation of our first carbon dioxide in the rate limiting step of consuming the pyruvate, and then the oxidation of the remaining disulfide, of the remaining thiol bonds to produce disulfide bridge to allow us to regeneration and accept more of the hydroxyethyl TPP. So basically, this is an illustration of how three enzymes who are working in very close proximity in near covalent interactions to allow the safe passage of electrons to move through, to go through the process of oxidation of a thiol to produce a disulfide, and allowing a displacement reaction using a thiolate interaction to give us the acetyl-CoA that we desire. In this particular process, it increases the efficiency, decreases diffusion of the enzyme products, i.e. substrates, and basically keeps the reaction very local. So it's an illustration of substrate channeling in regards to the intermediates actually never leave the enzyme service. They're basically handed off to each of the other individual enzymes in the particular pathway to increase the efficiency. And I've kind of illustrated it here a little closer in regards to the pyruvate carbon dioxide through the E1 complex. The E2 complex is giving us the consumption of CoAsh to make acetyl-CoA at the expense of consuming NAD plus to make NADH plus protons. And again, that little guy there is going through the process of oxidizing that disulfide to allow the E1 complex to pass on the material of the two carbon constituent that's remaining, the hydroxyethyl component, to actually the lipolysate enzyme arm to allow that to move through the whole process. So again, keep this in mind, be able to think about this illustrating and understanding what is happening. But the important thing is, this is the gatekeeper, it's the rate limiting step, and it's the first production of carbon dioxide from the carbon backbone that we've seen in the 6 carbon constituents as in glucose or in fructose, okay? So we've gone through that whole process in glycolysis. This is the first release of the carbon dioxide. Okay, so I'll stress again the lysine residual arm on E2, the dihydroxylipotransacyl enzyme, which gives us this oxidized, reduced, and acetylated form to allow us to participate in that particular high energy reaction, to allow us causing the release of the acetyl CoA, which is going to be now the intermediate going in specifically into the TCA cycle. We're going to come back to acetyl CoA multiple times in regard to its production, its utilization in the rest of this particular semester's course. So keep this in mind in regards to the utilization of disulfide bonds, in this case a thiol bond, forming a thiolate and a thiol, and then going through the process of oxidation. So again, keep that in mind. So we know thiamine pyrophosphate is very important in this reaction, and that's why it's actually substituted in a lot of fortified foods. Thiamine pyrophosphate, or TPP, has this capacity to interact with a number of enzymes, as it acts as a little bit of a electron sink in this particular ring. Now, if you do not have thiamine or thiamine pyrophosphate in your diet, there's actually a number of neurological and cardiovascular disorders that you can actually get. Beriberi is actually the main one in regards to having this particular deficiency. And this basically damages the nervous system. There's usually a lot of pain in the limbs and weakness, and shaky knees, and the legs raise up automatically, uncontrollable. And beriberi is Dutch for walk like a sheep. Now, I don't know how sheep walk, really. Most probably kind of stagger a little bit because of their little legs and their large bodies. But I think that's how they basically equated the disease from an observational purpose. But ultimately, what it does, the thiamine pyrophosphate is essential in the activation of aldehyde units and allowing their transfer, becomes a prosthetic group, particularly as we've seen with the pyruvate dehydrogenase complex. And we need that cofactor to allow us to adequately transfer the pyruvate to acetyl-CoA. And again, we are relying on this acetyl-CoA production in the form of ATP in a localized state, or we're moving glucose as a fuel source to the brain to allow it to do its job in its own mitochondria, to allow it to produce ATP locally for the brain tissue. So again, got to keep thinking in regards to the downstream track of what we're looking at in regards to maintaining a homeostasis of ATP and utilizing glucose, particularly in this case in the nervous system and in the brain. So let's have a look at the condensation reaction that's occurring within the TCA cycle. And it is a number of steps, as you can see, in regards to how we need to really manage this particular system and get the most out of it. There's a number of reversible steps and non-reversible steps also. So again, think of our clock face: 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock position. So we first bring in our acetyl-CoA, which is a 2-carbon constituent from the decarboxylation of pyruvate, and it's going to condense via an enzyme called citrate synthase in a one-directional system. It's going to condense with our old friend oxaloacetate. So oxaloacetate, which is a 4-carbon constituent, is going to condense with a 2-carbon constituent with this CoASH enzyme, being the great leaving group as it is, to interface with this particular bond to actually break the double bond to make this a alcohol and attach this guy to it in regards to the position. So you can see where it's in the mauve position. Here's the acetyl-CoA, here's the acetyl group coming from pyruvate, and it's now producing the compound called citrate, which is 6 carbons in length. This is known as a condensation reaction in regards to the oxaloacetate and the acetyl-CoA through the citrate synthase. Once you have that particular citrate, we can go through a dehydration reaction, because what we're going to do is cause a rearrangement of some of these particular bonds. So we have, again, 6 carbons all the way through to this position here. So we're going to go through the anaconate, cis-anaconate, in regards to a dehydration, but then we're going to go through a hydration reaction. So we're removing water and then replacing water in another position to give us a different orientation in regards to those double bonds, as well as the in the intermediate, but also the positioning of the carboxylic acids within the alcohol framework. So here we're seeing basically this guy here being transformed to a hydrogen, and then having this guy here having another group attached to it in the form of oxygen and hydrogen, so becoming an alcohol. So basically transferring this group to this group at the expense of this particular alcohol positioning through a simple dehydration and rehydration reaction. So in this case, what we have is basically a rearrangement to form isocitrate. Now, isocitrate becomes then our first constituent, which is going to give us the capacity to go through and release carbon dioxide. So it's a 6-carbon constituent to start off with, isocitrate. And it's going to do that by releasing carbon dioxide through the isocitrate dehydrogenase complex. My mistake, through the isocitrate dehydrogenase. And that expense is also going to be causing the release of protons and electrons, which are going to be sunk into NADH. So this is where we're making that NADH currency, which is going to go into the oxidative phosphorylational system. But we've now gone from isocitrate to another compound called alpha ketoglutarate. Glutarate. That should ring a bell. And here we have a keto group on it. So again, there's something here about like a similar amino acid. We'll come back to that later on. This one is an illustration of where it's now a 5-carbon constituent, because we've lost 1 carbon dioxide and 2 molecules of oxygen in regards to the rearrangement of this particular molecule, which is happening basically in this position and in this position. So this is where we're losing that carbon dioxide coming from. Okay, and we'll see that a little later on. So with the isocitrate dehydrogenase, we produce an alpha ketoglutarate. This is now a 5-carbon constituent. Now, through the alpha ketoglutarate dehydrogenase complex, which is a similar system to what we've seen previously with the pyruvate dehydrogenase complex, illustration of channel substrate movement, we're going to utilize coenzyme A as a component to give us a CoAsh component, a great leaving group. But this is going to be at the expense of also releasing carbon dioxide. This is known as an oxidative decarboxylation. So with this particular system, we're also going to see increasing the NADH pool and causing then the release of carbon dioxide. So you can see we're now down to a carbon 4 constituent. So we're going from a 6 to a 5 to a 4, from the 3 o'clock position to the 6 o'clock position. In that 6 o'clock position, we have succinyl-CoA, which is a 4-carbon constituent. And interestingly, it is going to go through a reversible reaction through the succinyl-CoA synthase enzyme. And in this case, we're moving it this direction, where we're going to basically be consuming GTP, or a form of ADP, to make GTP or ATP. So we have our ping pong system. So this is where we're getting our GTP, ATP equivalent from, but also causing that release of that coenzyme A, which is going to be able to give us the energy transfer to allow this reaction to occur to produce succinate, which is a 4-carbon constituent. Notice here between our 5 o'clock, well, let's say 4 o'clock and 6 o'clock position, that these reactions are not reversible. They are commitment stages. And we're going to come to this particular guy very shortly in regards to his commitment stage, because we can take this off as a potential precursor for some biomolecules. And again, we can commit ourselves to doing that depending on the needs of the cell. So let us continue our process in the citric acid cycle. Succinyl-CoA, which is a 4-carbon constituent, gives us the capacity to have that succinyl-CoA group as a leaving group, to go from a carboxylic acid feature or a double bond to a simple carboxylic acid. And now we've got succinate being produced, which is a 4-carbon constituent. In this case, we have a little problem, because look at the symmetry of the molecule. So we have carbon dioxide, we have a CO2, NH2, NH2. So we've got some level of symmetry in regards to this particular action. So the next reaction is the succinate dehydrogenase, a reversible reaction. This one is the only one that allows us to produce the FADH2 in a reversible process. So the dehydrogenation reaction gives us the capacity to form this double bond between these two central carbons. It's still a 4-carbon constituent, and it forms then the compound called fumarate. Now, fumarate is going to go through a fumarase with a hydration reaction and a dehydration reaction, so similar to what we saw over on this side through the anacontase and the anacontate production as an intermediate. So in this case, we're going to see the addition of molecular water to allow us to have one hydroxyl group positioned in one of the carbon constituents on the backbone, and then allow the dehydration process to then form the double bond. So we're going from a aldehyde to an alcohol to a carboxylic acid, in this case to a double bond constituent. Still 4 carbons in length, and our friend oxaloacetate. So in this case, we've gone through succinate to fumarate to malate. Now, we've already introduced you to malate through the malate shuttle, and we'll talk more about malate a little later on. Remember, we can bring that malate through, ideally, to the cytosol of the cell to make also oxaloacetate and phosphoenol pyruvate. So again, this is why it's called the hub of life in regards to the various mechanisms of these particular substrates that can go through. So again, we've got this 4-carbon constituent oxaloacetate, and we're going to be able to then reprime the system with more acetyl-CoA coming in through the citrate synthase, a non-reversible reaction, a commitment state of that 4-carbon, 2-carbon constituent to produce citrate, the 6-carbon constituent, and we can go through the whole system again. But again, we have formed 3 moieties of NADH, 1 moiety of FADH2, and 1 moiety of GTP equivalent to ATP. We've also seen the expense of 2 carbon dioxides. So we have released 2 carbon constituents. But as you'll see, we have not really touched still, by going through one single cycle, we have not fully degraded every single carbon in this particular incoming acetyl-CoA that is coming in from the TCA side, from the glycolytic cycle. So let's have a look more closely at these particular systems. So the citric acid cycle has 8 steps, and you need to know these. It has the first reaction of the acetyl-CoA coming in with the oxaloacetate, and using molecular water causing its displacement of the acetyl-CoA to actually then produce the citrate through the citrate synthase. Now, it doesn't produce an intermediate compound to produce this. We're not going to go through that because it's a little more complex. But the main thing is this highly exothermic, exogonic reaction in regards to that thiol ester intermediate gives us this capacity to cause a structural rearrangement to produce the citrate. Now, the concentrations of oxaloacetate are always maintained small in their overall place in the reaction because it's always being consumed, always being supplemented to be moved out of the TCA cycle. So with that small acetyl-CoA and oxaloacetate, well, high concentration of acetyl-CoA, small concentrations of oxaloacetate always drive that reaction forward to produce the citrate that we need in the TCA cycle. But again, this oxaloacetate has a point of regulation. So there's no real net removal or consumption of acetyl-CoA because it's always being regenerated or being supplemented or coming in from elsewhere. So there's always a little pool of acetyl-CoA, so there's real no net movement. So we only need a small amount of this to keep the reaction going because it's continually being recycled and turned over in its own particular little reactional system to keep that concentration of the production of the acetyl-CoA oxaloacetate produce the citrate. Now, this particular reaction, a delta G prime 0 of negative 23.2 kilojoules per mole. So you can start seeing there's some significant energy being released by these particular systems, which can drive other biological systems, as we will see. So the dehydration reaction, when we get to that particular citrate component, is utilizing the two protons and the two protons and an oxygen, the alcohol and the hydrogen moiety here to give us that double bond in this position. So the dehydration reaction gives us the cis anaconate in that particular role, and then the rehydration gives us the capacity to rearrange and swap these over. So again, hydration comes in and allows us to produce the isocitrate with the oxygen here, or the hydroxyl position here, and the hydrogen there in comparison to the citrate. So again, isocitrate and citrate are different based on their positions of their hydroxyl and hydrogen constituents on the carbon backbone. And we go through an anaconase reaction with a dehydration and hydration reaction to get that particular movement going through. Now, the interesting thing is this is a reversible reaction, and we can move citrate and isocitrate between each other. And we want to do that because we are going to utilize these constituents to allow us to make other compounds. But the problem is isocitrate is a dedicated component to move very rapidly into the next stage to go through the alpha ketoglutarate production. And with that, we're always going to see a very small concentration of this being present unless there's a inhibition of the alpha ketoglutarate dehydrogenase complex to then cause a increase in this particular concentration. But the interesting thing is it takes positive energy to do this. 13.3 kilojoules per mole. So again, we're going to have to get that energy maybe coming from the previous negative phthalate ester release in regards to the acetyl-CoA condensing with the oxaloacetate to produce the citrate at negative 32. Is it negative 32? Negative 32.2 kilojoules per mole. Now, we know this happens because in the dehydration-hydration reaction, we can actually use a fluorocitrate constituent. Now, fluoride moieties are very well known to stabilize enzyme complexes, so they become substrate inhibitors. So they become competitive substrate inhibitors specifically. In this case, we have the fluoroacetate producing the acetyl-CoA fluorate component. But what happens in the production of the fluorocitrate, that fluoro group basically screws up the whole reaction. It does not cause itself to be released from the enzyme, therefore acts as a competitive inhibitor. So by understanding that, we can figure out why and how this particular system works and what it's doing to the individual substrates coming in, because we can inhibit it and then examine that inhibitional process. Because we can use also radio-labeled fluoride to give us indication of where it's still sticking or is in with the enzyme complex. So again, that might have been somebody else's PhD years and years and years ago. So the next stage is where we're taking the oxidation of the isocitrate to citrate. And this is a really important reaction which goes through a number of particular forms. It goes through an oxidation and a decarboxylational reaction. In the isocitrate dehydrogenase, we're going to use NAD and NADP as the electron sink, allowing us to cause the rearrangement of these particular molecules. The first thing we're going to do is reduce this specifically to produce a double bond within the particular enzyme cleft, coordinating it with a manganese ion. And basically what we're going to see ultimately then is the decarboxylation of this particular constituent coming off in the reaction and giving us that capacity to go from a 6-carbon constituent to the 5-carbon constituent in the form of alpha ketoglutarate. So as we see in our pathway, there is just one simple step of reaction, a non-reversible reaction in the isocitrate dehydrogenase, but it's actually a multiple step reaction that allows us to cause the rearrangement of the carbon backbone as well as the removal of the carbon dioxide or the carbon constituent to be one less carbon in regards to having a decarboxylation to allow us to produce alpha ketoglutarate. So the oxidative decarboxylation now from our next stage, where we're taking the alpha ketoglutarate and going through a further decarboxylation to give us a carbon 4 in the form of succinyl CoA. Again, the alpha ketoglutarate dehydrogenase complex is very similar and homologous to the phosphate enolpyruvate dehydrogenase complex, has E1, E2, and E3, and basically goes through a similar structural component, but it has a specificity towards alpha ketoglutarate. So it's going to consume CoASH enzyme, it's going to produce NADH at the expense of NAD plus consumption, but cyclize it through the FADH 2 and FAD plus to cause that oxidation of that double bond on a lipolysine and allow that transfer to occur. So it's, again, a homologous system. So again, what we see is alpha ketoglutarate being decarboxylated in this lower position, and then having that thiol ester coming in to participate and allow that particular reaction to come through to allow us producing succinyl CoA. But again, with that decarboxylation, we're losing one carbon in the form of carbon dioxide, and we're left with 1, 2, 3, 4 carbon constituent from our remaining backbone. This particular energy system, minus 33.5 kilojoules per mole. So again, a substantial amount of energy being in the exergonic component, which can be then coupled with reactions that are not so favorable in those demise of biomolecules. Let's have a look at the next one, where we're now going through a process of the conversion of the succinyl CoA to succinate. So we're conserving our carbon number, but we're going through what we call a substrate level phosphorylation. And in this case, we're going to be actually depositing a phosphate group onto a nucleotide in regards to GDP, and using that inorganic phosphate to allow us then to utilize the energy coming from the succinyl CoA in the form of the CoASH enzyme to combine that inorganic phosphate with the GDP to make GTP. And again, that is equivalent to ATP. So in this case, we're breaking down a thiol ester bond, causing its release, using the energy to drive then the formation of GTP. And it only takes minus 2.6 kilojoules per mole. So we're still in the negative, which is good. And we're not consuming any energy in that particular process. Because really, with the succinyl CoA at minus 36 kilojoules, this is actually really basically promoting the synthesis of the GTP. But again, we have a consumption of positive and negative components, which give us an overall reaction of negative 2.9 kilojoules per mole. But again, with the nucleoside diphosphate kinases, we can go through that ping pong method. And if we need to make the GTP into ATP as a usable energy source, we can do so. And it costs us 0 kilojoules per mole. So again, we have the capacity to transfer the GTP into ATP and then utilize that ATP as an energy source outside this system in regards to the TCA cycle. So what we see here, again, is a enzyme-bound system in the sense of the succinyl CoA's synthase with that histidine moiety to basically coordinate succinate coming in, utilizing inorganic phosphate at the expense of the CoASH enzyme leaving group here to give us the phosphorylational component of the enzyme-bound substrate in its succinyl phosphated form. We cause then the release of the succinate and then the regeneration of the phosphate position onto the histidine of the enzyme. And it's that particular priming of that histidine that gives us the capacity now to take GDP, and make GTP and cause then the regeneration of the dephosphorylated enzyme histidine complex to allow us then to bind more succinyl CoA. So again, we see this particular situation where we're seeing now a transfer of a phosphate group from a substrate to an enzyme intermediate, which will then take another substrate and then transfer that phosphate group to make an energy carrier in the form of GTP, but also spitting out our next molecule in the form of succinate without no coenzyme constituents. So succinate is a symmetrical molecule, as we will see. So we're going to go through then from succinate to fumarate, a reversible reaction with this succinate dehydrogenase complex. Now this one is actually an enzyme cluster, and it's usually found in the inner wall of the mitochondria. So again, we're going to have some issues of some membrane spanning proteins anchoring this particular enzyme system in there and allowing us ultimately to take the four protons and its associated electrons to strip it to form a double bond in succinate to form fumarate and feed FADH2 with those electrons and protons to give us FADH2 at the consumption of FAD. So in that case, we're having that capacity to produce a very, very powerful electron carrier. These FADH2s are more pricey and more energetically favorable than that of the NADH. So these guys are the real hot stuff in regards to energy carriers. So through the succinate dehydrogenase, which is a reversible reaction, we're going to produce fumarate. And look, it takes us no energy to do that, which is great in regards to the movement of this molecule. So I want to make and bring to your attention now how the FADH2 is equivalent to a certain number of ATP molecules. So electrons through the process of NAD and FAD to oxygen, which is the electron acceptor, which is going to give us metabolic water, basically gives us 1.5 ATP molecules per electron pair. So I want you to keep that in mind. So because some of these electron carriers, FADH2 carries a number of different electrons to then that of NADH. So we have this capacity to change the number of electron carriers or the pairs of electrons coming through and response to the number of ATPs that are going to be consumed, ATPs that are going to be produced through those particular electrons. And we'll come back to that a little later on when we look at some of our balanced equations in regards to the consumption of ATP and the generation of ATP and how many electrons it requires. So one of our final reactions is the hydration reaction from fumarate to malate, taking minus 3.8 kilojoules per mole. And we're taking fumarate and we're basically going through a hydration reaction to break the double bond in this position to give us a carboanion transition state, a very short-lived compound in regards to wants to be protonated and allows that carbo anion to be stabilized by having a hydrogen bond being present. So we're going to see that through the fumarase. The fumarase does two reactions. That's one single enzyme does two reversible reactions to allow us to produce L-malate. Now, this is a stereo-specific enzyme, so it'll always attack one position over the other. And also, when we take D-malate, so if we change the orientation of our constituents to become the D form, it's not going to actually be bound to the fumarate. The fumarase is going to be able to distinguish between the L and the D form, and therefore there's an issue of substrate specificity and recognition by the chirality or the orientation of the individual molecule. Okay, so we're going to have these issues in regards to utilizing molecules that look similar to some of the intermediate substrates in the TCA cycle that give us the capacity to study this particular system. The malonate to succinate, the fumarate, and the L and D malates all illustrate capacity to interact with the enzyme and causes inhibition or not interact with the enzyme due to its stereospecificity. So again, we have these capacities to dissect this pathway by looking at the roles of inhibition in this particular system. We're going to leave it at that because I want to talk more specifically about the dehydrogenation of malate to oxaloacetate, because that will then complete our cycle. But I also want to emphasize the role of oxaloacetate in the TCA cycle and how we can move that off as a particular intermediate into other metabolic pathways. And we've already seen that when we look at the phosphoenolpyruvate. So go back and study that particular reaction with the pyruvate and the lactic acid coming in through the mitochondria, going through the intermediate of oxaloacetate, producing malate or producing phosphoenol pyruvate. And again, we've seen this reaction before. We've seen this particular system of oxaloacetate and malate playing a role. So we'll leave it at that, and I will now go to office hours, and I will see you tomorrow morning if you're not attending office hours. Bye for now.